ஆமாடா.
Yes, good evening. We'll wait for some time. Let the other join, then we can start the session. And today will be like for the course like 12th week last week, and one more session will be there. That will be we are going to wind up our revision session for the full what we have studied in the like last 12 month, 12 week. So we'll wait for some time. If anyone have any doubt or something that you can ask around, and today mostly we'll be dealing about the Monte Carlo simulation like uncertainty problems, and we'll go some application based. Like last week we have some application based, so we'll go for that one only. And before that, I'll just give the brief like what we have studied till now. And today I will be mostly with the physics informed that machine learning will be there. Like we'll be solving some partial differential equation or ordinary differential equation. And the second one, what we were having is the fin problem, like in that heat transfer. Then one more we have is the surrogate learning is there. We'll take some examples or we'll take some papers also. We'll try to explain like how can we proceed once we'll go with the traditional method. We need the specific features and all. But sometimes if we solve some that the typical that mathematical equations so that we need the FEM or CFD. And if we go with that finite difference method or FEM methods, it took some time. It's a computationally expensive methods are there. So what we can do, like we can just train the neural network, so it will be that the approximate that solutions will be there. Instead of the solving traditional method, we'll just take them as an input and then we'll going to solve the equations with the help of the machine learning. So it will be become that less expensive, like people are doing now. Even in the like it's application in engineering applications actually. Before that last class, like it was the application for the MRI and all, and actually this was the mainly for CNN that we have used because that the MRI is actually like what we call that the magnetic resonance imaging. So imaging that we can give as an input to the CNN model only. So that we have seen around CNN architecture we have seen before the like beforehand class also. So that's how the we have proceeded. So we'll see some typical example like in the core of engineering, like that the heat transfer or a computer fluid mechanics or even solving that for the mathematical background, like what we have that ordinary differential equations or partial differential equations that we have. So that will solve like that we'll see around and then we'll try to explain you like how it can work it out. We'll not go with the detailing with the codes. I'll show the codes like how it worked and all, like what need to be done, how to generate the data, to give the input, and like what are the factors that are going to involve and that what will be the output will be there. Because sometimes when we have some complex problems, we know the cause, we know the effect, but what is that like it's going to be a mapping. Mapping means it's a relationship, like how it going to relate with the input or the output. It's a bit of complicated, like we will do the grid or the that the mesh and all. So that will see from now itself. So I think we can wait for 3 to 4 more minutes and then we'll start the session. Before jumping into the application part, we'll see what is that like a structure, like a probabilistic that model what we have earlier. We have seen that the neo based classification. Even we have seen the generative based and then discriminative based and all. Then we'll see once we'll introduce the Monte Carlo, like what that uncertainty, like which it's called that the like that the Monte Carlo simulation. So we'll see around all the things for today only. Today like will be the mostly based upon the application wise only, and we'll wait for some time. We'll let the other join, then we'll start the session. As we can see, we are around like last week, and we have seen the last class like that encoder generative adversarial, that the network we have seen that. Today we'll see that structure like a probabilistic model. Then we'll see the Monte Carlo methods. I'll show like one unpublished work also, like how it will go. Before that, I'll just show uh, what is the content for this week actually. And one more what we have will for the Monte Carlo also there. So we'll show not exact the paper, but will we are in the 12th week. In the last class, like we have seen that maximum that likelihood estimation, then MAP was there, then the Bayesian regression we have seen around, and then we introduced the generative that model. It's actually a self that a supervised machine learning. Then auto encoder like that will be having encoder, then decoder, then it will be going to like that the replicate of what will give the input. Let's say I have the signals are there, and signal will be like very noisy and all. What we'll do, we'll try to figure it out with that. We'll give the input as it is raw signal, like after filtering and all. Obviously, that we have to remove the noise and all, and they will try to encode it, and they'll compress it, and then after once they're going to extract the feature within the system or within the signal itself, then they're going to decode it. Then we'll be giving the output, and then we'll be they will try to replicate as human and all. So then that one example that we have seen, that cardiac MRI segmentation and diagnosis, and then second was the like a TensorFlow code was there, like it's with the Python actually. So that MRI application actually, if what's happening, like MRI will be taking as an image, and and once we'll take the MRI, like that our that application part or that our point of interest, that so point of interest will be somewhere around like very specific. It will not, let's say I have 4 by 4 like a 4 by 4 of that image is there, or but we should not tell in terms of the but it will be based upon the pixel or maybe the RGB colors and all that we have to define it. But I'm just telling as a the vague language. 4f4 is this, but maybe our that point of interest will be somewhere around zero point 0.1 because that will be the effective part, or that will be the defective part that the doctor will see around. If we give the whole input to the CNN model, what will happen? It's going to become the computationally expensive. So what we will do, we have to point out where is the point of interest. Then we'll be going to take image as an input, like we'll be going to do the segmentation. After the segmentation, we're going to convert into after the segmentation, we're going to convert into once we'll do the segmentation. After the segmentation, what we have to do, we have to convert into the like a tensor. Like it's the matrix form of that image, because we can't give an image as an input either in terms of that should be in terms of the numbers. In terms of the number should be there. So that will be converted into the matrix, like it's again converted into the TensorFlow because it will be a three-dimensional will be there, and then it will be going to be like compress it, then flatten it, like they're going to will extract the feature. Then we are going to again come up with the that like expansion. Like the CNN, what they will do, will be going to take one feature, will be going to segment it, will be giving into the like flatten it, like stride, and then that other that what we have that hidden layer, that the block will be there, block one, block two, block three. Then it so then once we have compressed it, So we extract the feature, whatever we need the feature, then we are going to flatten it. Flatten it means like if we have to convert, like once it got compressed, we are going to expand it. Then once we have expanded, just 1 minute. Is my voice is audible? Seems to be my video. Fine. So once it's done, so then we can get whatever you know, and then CNN can be the classification model, or it can be like a regression model also. So both can be there. So we will be able to do classification. As we know that MRI, let's say one patient is there. One patient, they got some disease or some like let's say they got some injury in the muscles. So before the injury or before the data collections, what we took some data, we took the MRI. Once they have got the fatigue or some that the muscle alteration happen. So before the like initial MRI is there, according to that what we have the features are there, and once it got fatigued out, once it got any the muscles alterations came out, so we know the input and output both are there. So now we will be able to with the help of with the help of CNN, we can able to classify. Both can be classified. So that's how the things will be done. So here it will become the supervised machine learning. Sometime if it is the time series data will be there, so we have to do the regression. Let's say I have I have to check with the fatigue evolution, or maybe I have to check with the time. Like let's say I'm going to walk on the treadmill. That let's say I'm going to do the that sprinting, and I have taken the data, like I'm continuously taking the data, like that sensor is like connected on the somewhere biceps muscles or maybe the thigh muscles and all. So that when the person is going to like take part in activity, with the time how it evolves, and let's say in the starting that the muscle was fresh and they were having that enough oxygen was there, so we got very good data or something that we got very good like that the feature we got. Once they try to deteriorate with the feature, like fatigue happen, it got deteriorate, like their that activity or that intensity for the like things got down. So that we can do the like real time, that the monitoring also we can do. So that will comes under the regression part. So that's how the things was done in this. And then segmentation part we have seen around previous lecture also. Like previous lecture means in the third or fourth week, we have seen the like a detailed explanation of how to do the segmentation, where to do segmentation, what should be the size, and how can we define the that so that intensity or the pixel and all that we have to see around. So these were the last week. 10th week is some traditional methods were there that we have also seen around. So this week mostly will be going like how it will go. We'll be seeing a structure like a probabilistic model, and then the Monte Carlo methods, and then we'll be seeing the example like fin heat transfer, or we'll be seeing that like application for the CFD dynamics, like why do we need and all. I'll show you some that brief equations also, like how it will be bit of difficulty to solve in the traditional method. Like we can solve through. People have done it. People are doing also in the traditional mathematics also. But by the use of that the machine learning, that can be solved, or like it can be a less completely expensive can be there. Then third example, what we were having is the topology optimization. Topology is something like we have to, let's say, someone will be saying like I have to do the filling of the materials. Let's say like, or maybe the size optimization. If I'll go with the any of the shade of the buses and all, so they can doing with the whole structure will can they can make through the like a rectangular shape and all. But the thing is that we don't need, because it will become the bulky material, or that will become the material wastage and all will be there. So we can optimize. We can like that the material should be less used, and it should be a strong enough to study. Like it could be that, so that should be stand up. So it like optimization technique, like how to weight optimization, sometimes that material optimization, or maybe a topology itself, it will say shape of that. So we have to get the better shape and all of that. Okay. So then after we have the partial differential equations, or maybe ordinary differential equations, that if we have seen around in the 12th, or maybe that 11th or 12th, that we are solving the ordinary differential equation. So what we are going to do, we are taking that too many points, we'll be solving it, and then until it become there that the error will be that less, so or maybe that exact solution will be coming. So that will be that our exact. So it's going to be a iterative process. The same way that the same can be that learned through the machine learning, and it can be solved through that. Okay. So now we'll go back and we'll see around what is the actually. We'll wait. I'll switch off the camera here and we'll solve it here. So I think I don't need to do the again the full course or brief and all. The tomorrow we'll see. The tomorrow that lecture will be around somewhere around just one. Tomorrow 6 to 8 p.m. will be like it's something like extra session. In that will be I'll be taking like mostly starting with the linear regression and the code like all that neural network, deep learning, CNN, and after the CNN, what we are having that RNN and then CNN plus LSTM. This was the whole part of neural network. Then what we have the traditional methods are there. Traditional method what we have is the Bayesian regression, decision tree, random forest, SVM, naive based classifications and all, and then K means, and then KNN, then the Gaussian model mixture are there. So this will be the traditional method. When what we have the some advanced techniques are there like that today we'll see this, like this one and this, for this also we'll see one code or maybe I'll show you one paper actually to see exactly how it going to work it out and all. So now we'll see just 1 minute. Not saved. Huh. Okay, so now we'll come back to the what is the structured probabilistic model. Earlier, what we used to see earlier, what we used to see like we were used to see like it's a deterministic model. Like all the model like it's the CNN or maybe that traditional methods and all it was all deterministic. There is no change. There is with the time or with the circumstances with the activity it will not change in all. But if you see in the real time model like real time applications all it will change with the circumstances. It will change with the time also or even the like that uncertainty will also comes into the picture. So if we go with the traditional method, it might be not able to give the clear picture, or they'll be either try to overestimate or underestimate. Means that model might not be that optimized model. So in that case, what we have to do, we have to introduce the uncertainty, or maybe that any probabilistic model. So they are going to deal with the input and output. Like it should be have that so that they should take the history from the previous also, or even they can take the future also. Future like properties also. Just 1 minute, someone want to join. Okay. So what we have to do, we have to check with the we have to make the prediction based on the probability distribution rather than their absolute value. Rather than their absolute value. So like if we don't incorporate this one, If we don't incorporate this one, so what will happen? They will try to either overestimate the results or maybe underestimate the results. So it will be not giving the accurate one. Like so, to incorporate the probability, it will give the accurate understanding of the complex system. So what is the exactly probability model is actually we are going to learn the pattern data and make prediction on the new unseen data. It's like we have to make the prediction like on the unseen data. So it like we'll be having previous history data also, and then we are going to train on, or either we have to do the testing on the unseen data also. So they are actually they're like a statistical model that capture the inherent uncertainty in the data and incorporate into the predictions also. So that's what the concept of that Monte Carlo will comes into the pictures. Man, Monte Carlo will comes into the pictures and all. Okay. So actually, then they are going to their application is going to use in the speech recognition or maybe that recommendation system. So and that nowadays like recently I can say like people are going more into the uncertainty uncertainty like aware model, because that we all know that in any of that real time application, either in that going to capture that our that is the heart rate system or the fatigue modeling, or even for the case of that forecasting of that that weather also forecasting of that flat rate and all something. So it going to they will be having uncertainty. So we have to incorporate, we have to take care of all these things, otherwise that will not able to get the proper pictures of that. So, what are the types of the probabilistic model that what we have? It's a first one is the generative model. What we'll be having, we'll be taking the previous data, train the model, and then we are going to regenerate the data based on the previous history. And then what we have is the discriminative model. Discriminative model is something like if we go around, like in the generator, like GAN. So what we were having, we were giving the data like it's a fake image, and we were giving the real data. We were having the like uh, generation part. Once it got generated, so we were having the discriminator. Then we have to make the prediction either it's whatever it's the fake data is that it's coming close to the real or not. If it is not, again we are going to feed into the like generation part. It will become the cycle. It's like a generative part. Like it's become cycle until unless that the error between the real or fake, it will become the very minor, that the error, or maybe we'll say construction loss should become l- like minimum. So this is the based upon the construction, that is the like generative model. It's a like that can be combined in the DNA. Then third one, what we have is the graphical model. Graphical model is something like we have to make the interconnected like results and all. Let's say if I'll say like I'm going to run and all. Let's say so we'll take some muscle activity. Muscle activity, it's one alone muscle. It's not going to take part. I'm going to run. It will take the hand muscle, the thigh muscles, leg muscles, and all. It will come. So we have to take the graph. We have to make the node one, two, three. It will be interconnected based on the graph. For that also we have one pictures actually. I'll show you how it will look like. So what is that graph theoretical modeling of the multi-scale image dynamics? What we have done, we have taken one data collection, and in that we have three muscles are there. So for their three muscle, we are going to create a graph. Will not show the exactly how it look like, how the graph will be look like. So we can see around here. So it's the three muscles are there, both are interconnected, like how much that information is flowing from the VL to VM, VM to RF, and then RF to VL, or either way it can go. In the either way it can go, like so how it will look like. So that's how the things will go. We have to make the graphs, and then we have to analyze it like how it will go and all. Okay, so we'll come back to the again our so in genetic model, it will be going to be a joint distribution from the input and output. This model like generate a new data based on the probability distribution, like let's say conditional probability. Like a probability. It's like a from the like it's going to reconstruction. Genetic model are powerful because they can generate new data that resemble the training data. Like it's going to copycat the training data. So that can be used for the language translation and then text generations and all. So for this, I think the ninth or 10th week lecture you can go. So you can check it out. In the discriminative model, it's be based upon the model condition distribution, the output variable given the input variable. So they are going to like differentiate, like they are going to decision boundary that separate from the different classes of the output variable. So like it's something instead of that directly getting into the like CNN or maybe that KNN and all, they're going to create useful when the focus on making accurate prediction rather than the generating the new data. So that can be used for the image recognition, speech recognition, or sentiment analysis. Graphical model, it's to use the show the conditional dependence between the two variable. Let's say for the quadriceps muscle, we have three muscles. First one is the rectus femoris. Second one, what we have is the vastus medialis. Then third one, what we have is the vastus lateralis. So now we want to see that how it's going to depends from the one muscles to second to the third. Like it's a interconnected theory we can make. So they are commonly used for the tasks such as that the image recognition. Then we have the NLP, like it's the natural that language processing, and then casual interference and all. So this is the thing, like this is the model that what we have. So this model we didn't went to the detail like this we don't have like just to show like how it done. This we have done for the GAN. You can go through the last week lecture or before the last week lecture you can go around. Discriminative model is simply we can say the traditional also like ANN, CNN or KNN or random forest and all that you can go around and all. So now we'll come back like this is the things that we are having try to generate, try to discriminate or that how the data is going to look like. Like it's a interconnected and all. So now once we are going to having uncertainty, what we do, we once that things will change with the time, things will change with the activity. So we have to do the Monte Carlo simulation. So Monte Carlo simulation is actually used to predict and understand the behavior of the system where it going to having some uncertainty. It will be having some uncertainty. So what they will do, they're going to do the running the multiple simulation with the random input, and then technique it's going to help to possible outcome and their probability and all. So means it's not like let's say I am running some model. Let's say some features they have the some thousand variables are there or thousand like data inputs are there. So now what I will do, will try to either add the noise. It's that what we call in terms of the machine learning or signal processing. It's the white noise. We'll add it, and then we'll see once we add the some noise or we have removed some data points, whether our model is going to give the same results or not. It's something like a uncertainty aware the model what we have. If it is coming close to the original model, it means that our model is stable, they will giving the better results. Okay. If it is having too much variations, it means like it's a they are having much impact is coming when once there are going to be some uncertainty or maybe some that noise will comes into the picture. So this application will be having more impact into the digital like that the healthcare systems and all. What's happened? Let's say I have some watch is there, and they're going to measure the pulse rate or maybe the heart rate and all. So what will happen if we are going to add some noise or some external factor is going to create more impact? What will happen? That the digital watch or maybe that smart watch will not give the accurate result. Means that so their error will be more. So we'll not able to trust the data whether that will be going to, this one giving the best result or that other smartwatch is giving the best result. So it means we have to just check it out on the real time system, then we have to give it out. So in that, instead of relying on a single solution, it generates the many different scenario to give a clear picture of the range of the possible results. Just 1 minute. So what will happen? So let's say we have the one examples is there, like we are going to flipping a coin many times to find out the likelihood of the heads or tails or move or more the flips. Okay. So more the flip, clear the probability will becomes. Anyway, once we are going to coin the toss or flip the coin, it will become the either head or tail. The chances of the 50% will be there. But the thing is that for some certain coins or something like we can get more clear pictures of that. So it is actually used in the field like finance or maybe the engineering or science applications also, or mostly I can say the medicine or healthcare application. Because that people are coming up with the some smartwatch, or even now they are coming up with that they're going to keep that is the heart rate monitor on the chest, and then they're going to take track the data of that ECG data with the without doing any cardio that traditional methods to do it and all. So with the help of the heart rate itself, they're able to generate the ECG data and all. That's the things like it should be having, with the time it will change, or their probability will become more clearer and all. So how it will going to work it out? So these are some steps are there. First, we have to identify the system or process we want to simulate. Okay, this can be of anything from the stock prices to the engineering model. Let's say I'm going to do the cardio ECG data. Then after, choose the right probability distributions. Like let's say what the uncertainty, like how it's going to happen, like how much data we're going to remove it, and then when we're going to add some some noise, which distribution there's so they are following on all. So means we have to find out what is the uncertain parameter in our model. For example, for modeling of the stock prices, we might use the normal distribution. Like they're going to follow like this one to represent the price fluctuation. So then after, generate the random input based on the chosen probability and repeat the process many times to create the variety of the possible scenario. Like we have to run simulations based upon the input what we have given the probability. Then we are going to do what are the some possible cases can be coming. Then after we have to uh, analyze the results. We'll get some sort of distributions by looking at these results. We can make informed decision based on the possible range of the scenario, just a single expected outcome. So What will be the that some sort of mathematics behind of that? So the main goal of the Monte Carlo simulation is to random sampling estimate to expected value of the. We'll be doing the random sampling. We are going to do the random like random simulation, but we want to get a expected functions of that what we are having the exact the model what we have. So for a given function of fx for a domain D, expected value of a that e of fx can be estimated using the following formula. It will going to be like normal like estimations will be there. So nx is the like something is the like random sample. Xi is random sample from the domain D. So what they will do? Monte Carlo helps to estimate the integral when exact solution is hard to find. So what they will do? They are going to adjust the size of the domain. Means it's the volume of the domain, or they'll try to replicate, or it should come closer to the what we were having the previous that the results was there. So, what are the benefits are there? It's going to first one is going to be a like risk analysis, or it can be help in the that making the better decision making, or flexibility across the field, or maybe the handling the complex system, or visualization like a visualization of the uncertainty. Also, we can check around. So, what is the like some sort of limitations we can see? So it's a computational intensity. Like we have to run that is the like that the million that the million types of the simulation. Like we have to do the plenty number of time. Like they read like significant times of resource, especially with the complex model and with the multiple simulation. Then again we have to like depends upon the quality of the input data. If the data is the poor, then will become the like unreliable that un like reliable results can comes in the picture. Then conversion rate high accuracy often like needs the larger number of simulation, especially for the rare events. Sometimes they will do the oversimplification, may miss the complex system, or maybe they'll be giving the overfitting also. Sometimes underfitting results also. So I'll just show one example like how it's going to work it out, how it came out. Just 1 minute. I'll just show here how it look like. So the thing is that what we are having the uncertainty aware deep temporal learning model. So that whole methods, what is that what we have? We are having the data acquisition. We have done the pre-processing. Then we have taken the image in the form of a scalogram, and that scalogram will look like this. Then after we have introduced the like we have done the regression model, then feature extraction we have done. Then we have used the MC dropout, like Monte Carlo dropout. For that code is also there. I'll just see the codes where it is, and then I'll show you. Okay. So this one is data actually. We have to that load the data. Like data can be terms of anything like before that only I have done the pre-processing and then created the image, or even created the CWT also. Then after scene and feature extractions that we have to give the input layer. Then a convolution layer will be having the 3 of 16 padding will be there. Then we are having that ReLU layer. Then pooling will be there. Again, second that what we have the layers are there. Like it's a compressed zone. Compressed like we are having the compressed, flattened. Then expansion will be there. So in that we have the three conventional layers are there, and the maximum pooling layer is the 2D layer we are using. Then we are going to use the flatten layer. So this is the all same like 64 that the number of that the units are there. Then after like they're going to train the like CNN model, and for that we have used the that Adam optimizer. Then we have the like epoch size of the 15, then the like batch size of 32. So once the feature got extracted, so we have to give the temporal model. Temporal models. Why do we need to give temporal model? Like we are having the for the regression problems. Once it's done, so we have to do the training. Once you have the like done the training, so it's 0.8 times, like 80% of the data is going to use it for the training, and then 20% is going to use it for the testing, and all will be there. So once we have done it, so we have to give the dropout model. So what is the dropout model? It's a 30% of the data we have removed it, like MC dropout, like it's the data we have taken 0.3, 30%, and then again the same thing, like we have to give the same model, then train it, then MC dropout, the prediction results came, and here it's going to take out the results, and then we'll be giving the uncertainty like based upon the reliability also, and then we are going to plot it. So once you plot it, that the results will comes like this. So it's a exact line, like that the ideal line, then we'll be having the there data distributions will be there and all, and will show the what is the look like scene in architecture. So in the scene architecture, we have given the input as a scalogram unit. Then we have the three convolution layer. For the first one is the 16 is the like their size. Then 32 is the size. Then convolution layer for 64. Then we have the like pooling size of the 2 by 2. Then we have done the flatten. Then the dense layer. Then dropout. Then output came. So then LSTM is nothing like whatever the results came from the scene architecture. We have given the LSTM that is the layer, then the like a dropout, then the will be giving the RT. RT is the like remaining estimate time is there. It's the things like that I was working on that. So that's how the things came out of the picture. Now we'll come back to the our that model will go. So now we'll be seeing whatever like till now what we have seen around like we have seen around that structure. So when there is some sort of changes, like we will be having some chances that things will get changed. So it's probabilistic. To deal with that, like how much percentage change came, or like how much data we are going to remove it, or to add it and all. To deal with that, what we have is the Monte Carlo simulations are there. So till now, what we have seen around, like started with the linear regression, then we went to the neural network, then we went to the deep learning. In the deep learning, we have seen the CNN, LSTM, and after that, what we have seen around, we have get traditional method like supervised machine learning. Then we have seen around the unsupervised machine learning and like self-supervised learning also we have seen. And we have seen around the ensemble learning also. It's like a bagging and boosting also. Then we have the advanced machine learning technique was there like GAN, like auto encoder, then structure one, then probabilistic. So we have seen around the whole. Now we'll see the overall application we're going to that use. That the last class that we have seen or like it in lecture it was the MRI MRI image of the cardiac application. So now today we'll be seeing some how it can be used in the that, so that the mainly engineering application. So what are the types of the application? It can go the surrogate model. Surrogate model is something instead of solving the some physics based formulation or maybe the equations and all, we can create a surrogate model, like it's a approximate model. It's a approximate model based upon the physics, where in that physics based model it's going to be slow or impractical. If we go with the container mechanics, or maybe that quantum theory also, we have to work on the that the nanoparticle or maybe the size of the atoms and all. The things will be that once we go with the traditional method CFD or FEM or the DM methods, it will take more and more time. Okay, so it will take more one time. So we can create a surrogate model. Surrogate model, by the name, it's a surrogation we are doing. Like it's something replication, or it's the placement or that replacement of the something that existing model what we have. So that can be used for the inverse problem also, like effect to cause. Just 1 minute. Very quick. Effective cause, like in that like in general what we used to see what is the due to the cause, some reason, what is the effect. So here we can do the inverse problem also, like we but for this particular effect, what can be the reason, that will be actually help in the diagnosis model, like for the doctors, and can be used for the optimization also. And then even we can use for the modeling of the unknown physics, like when we know the input, we know the output, but we don't know the mapping of the model, like how it relates from the input to the output, but we don't know like what is the parameter it's going to influence one from the second one, second to third one. So in that case we can use the surrogate models and all. So then even we can use for the like directly solving the differential equations, like a partial differential equation or maybe ordinary differential equation. Even we can use for the optimal control also. Okay, so now we'll see one example. It's a typical mechanical example for polymer heat transfer of the fin. Fin, if you have understanding of that, how it's going to work it out. So let's say, I have that this one heat is there, and there some process is going to happen. Heat process will be there. So one can give the like I have to transfer the heat, so let it go open. Like I'll leave it out. This wall will be act as a open like exposure to the atmosphere. So that will going to transfer the heat. But what will happen effectively? So due to the transfer of the heat from the surface itself, it's going to impact the whatever the wall of that working system is there. That might create some problems and all. So what they will do, we'll be having either one more problem. So we can extend the structure, and then slowly it will transfer the heat, become the surface area will be the more. So one can be like it's the very conventional method, but the thing is that but the thing is that so that the heat distribution will be not always the same like for the all. It's going to make some counter like this. Here the maximum. Once it go with the length, it's going to slow down. It transfers of the heat. So if we give the this much extra material, so this will become the wastage. It will become the wastage. So what we'll do, we are going to make a create a fin. It will be having some parabolic shape or some like thermal shape and all. So we can create it and all. So that's how the things will go out and all. So that's why the concept of topology optimization will comes into the picture. So I will give just brief of that how their physics will look like. Okay. So if you see that in many engineering application, like heat exchanger, and electronic cooling also, and biomedical devices that fin used to enhance the heat transfer. So the like idea is to how the temperature is going to vary along the fin, and how much the heat is dissipated. So the thing is that we want to predict what theta of x, like temperature change, T of x at any location x minus T of infinity. Like T infinity is actually a ambient temperature. Okay. So and x will be the position. So for this, what we have the physics model is there. If we write the governing equation, it's something will be d theta square by dx square minus m square by theta is equal to 0, where m is equal to heat, like convective heat transfer coefficient, p is the like a perimeter, k is the thermal conductivity, a is the area. So like I'll write it also. Heat transfer, p is the perimeter, k is the thermal conductivity, and a is the cross sectional area. So that if we see for this analytical solution is actually what is that cos of h m into L minus x, that is the length of the fin, upon cos of h m of L. But the case of it will going to make some assumption, make some assumption like that the material should be homogeneous and then cross area should not change. But in the real time, it will change the material property with the heat also and all. So what will happen? So in the real case, the material property will, even that the heat transfer coefficient will also change. And even the cross sectional area also will change and all. So we'll take some extra page and all. I'll just do it. So that exact mapping will be for the four Machine learning will be the exact mapping. X is the position of the fin. H, convective heat transfer. K, the thermal conductivity. And even with the geometry also. So what will be there? F of X, H, K, all properties, how it going to transfer will be there. Okay. So for the ML, the input will be what? X will be as X, H, K, geometry, some other parameter can be there. And the output will be what? Temperature distributions. So for this case, we can use the simple regression model. I'll show you the one example actually in the MATLAB. Fin problems. So we can see that I'm going to generate the, let's say that the length of the fin is the 0.1 meter, like it's taken in that one only. And that we are going to generate the data, like that linear expressing of the 50. And the convection heat transfer we have taken of the 50, like it's all standard that going to be a unit. And K, thermal conductivity is the 200. And that the perimeter is 0.02 and the area is the 0.001, that's going to be like meter square. And T of infinite, like ambient temperature, it's going to 25 degrees Celsius. And T of base, like let's say I have the fin size of like this. I have the fin, let's say this one, and there this is going to look like fin. So that base temperature, T of base, they've given 100 degrees Celsius, and T of ambient is given 25 degrees Celsius. So this is how things will look like. So what we have to do, we have to do the theta of b like T of base minus T of infinity, and then m, like m is equal to square root of the h and p by k into a. So we can see the analytical equations are like like theta is equal to theta of b into cos of h m into l minus x cos of h m into l. Then T is equal to theta plus T of infinity, like a base temperature. So first we have to generate the plot, like how the like generator like the like that temperature is going to distribute and all. Then after we are going to create the data set. As we don't have the exact data set, so we have generated through the x and h of ones from the n natural number and k of ones in the n natural number. Then y data is equal to t. So then we have like trained the regression that the model with the using that ls boost, like logistic boost and all. And we have taken the number of learning cycles is the 100, and we have predicted through the model of x data. Then we have done the comparison between the actual and then ML data prediction. So we'll be going to generate the two picture. So we can see around, first one is the temperature distribution, like how it going to fin at the base. At the base, it's going to maximum temperature. Once it went to the till of 0.1 meter, its temperature got down. It came to 84 degrees Celsius. It was 100 at there, but at the end of the fin, it became point. So now we can see ML versus physics, that is a physics model. This is the actual model. So now we will be able to, with the using of the machine learning, initially some error was there, some error was there. Now we are going to see around, like it's going to perfectly came around. So instead of solving the analytical equations and all, we can give the directly to the machine learning and we can get the results also. Okay. Second problem also what we have is the we can faced with data for the same problem. We have done it around. Then we have used some other model, like that the first one is the ensemble model, that SVM model, then that we have the decision tree model. Even we have the ANN model with the 10, that number of that the hidden unit. And then we have calculated the RMSE, MAE, like a mean absolute error, and then R square. Then we have plotted it. So same things that earlier what we have used, it was the only that logistic like regression was there, but now I'm going to use the different ensemble that model, SVM model, decision tree, and we have used around. For that, to train the model, we have used the 70% of the data for the training and 30% of the data for the testing. Now we'll going to run the code. So we can see around here. So we can see that the error for the ensemble learning is the 0.4313, and then R square is the 0.98, and then SVM having 1.1062, and then R square is having somewhere around point 0.1 0.912. SVM is giving the bit like a poor results. SVM, I'll be. So we can see around ensemble model that the error is 0.4313. It's a good, like we have the less error, and then good R square value is there. And for SVM, that the error value is more high, 3.7899, and then MA, and then that R square is not going to correlate, like it's coming 0.518. And the decision tree, it's also giving the poor results compared to the other model. And then we are having the 0.5 on it, and like decently 1.1062, and then comparatively compared to the SVM, this is giving the best result. And among of all this, what we can see around that RMSE of that, what we can say, like ANN is giving the very less value, and then R square value is 0.999. So it means among of all these four model, ANN is giving the better results. As we have seen around, like ANN tried to mimic the what the brain thinks. Then like SVM, they're going to create a hyperplane. Ensemble learning methods is also again creating a like multiple decision tree and then bagging. Decision tree itself, it's going to create the node and then a root and all. So it's giving but not compared to the what we have. So ANN giving the better results. And some pictures what we have is the model comparison. We can see around, so that ANN is having perfect, like it's coming closer to that. Decision tree having more fluctuation, ensemble having also closer to that one, and the so that the worst result is given by the SVM. And second, it's the error distribution we can see around. That's how the error was distributed. Third one, what we have is the residual plot for the ensemble cases, like residual, then predicted value and all came around. Then fourth one is the physics versus ML model. We can see around it's coming somewhere closer to the what we are having the exact physics, like a physics model. So this is the something like we didn't add anything, like is the actual model. Now what we can do around, we can add some noise. We can add some noise. So what we can do, we can add the, because once we are going to measure the fin thermocouple, there might be a noise that can be of ambient noise or measurement noise or the accuracy sensitivity also will comes into the picture. So it can be of like what they will do, model the noise will be T measure, T true plus noise, and that it's going to belong to the, you know. So we'll see one example of that. What we can say, one code, similar code means similar examples will be there with the noise. Same problem. We have the same problem, and we are going to use the theta and then how we calculated 2 theta. But here, what we have done, T true is the theta plus the and all. Add the noise. It's the point 0.5. Adjust the point 0.1 to like a 0. Like that, the noise will be noise level into random size of the T of true. T noisy will be the T true plus the T noise. What we have done the modeling. So that noise level we can do the, if we want to add the 0.1% or 0.2%, 0.3%, 0.4% and all, it can go around. So then, so thereafter we can plot the clean versus noisy, that is the like distributions, and we have to do like data set, like it's a train on the noisy data. We have to like testing we have to do on the like what we have the data. Then we have to split the data with the like a 70 by 30. Even we can do the 80 by 20. It will change some results, and then we have to put the ensemble model, and for that particular model, we are going to calculate the RMSE value, that MAE value, that is going to that the mean absolute error, and then R square is a coefficient of determination. And we can see here that the prediction was a true. Then that the error, that the histogram, and then like residual plots also. So if we run, then how it come, we'll see. So we can see around, like once we add the noise for the same data set, like for the ensemble model, it was the zero point 0.4. Now the error got increased to 0.59. Earlier, the model we have run it for the ensemble model, that the RMSE value was the zero point 0.4. If we remember here, for the same model, I'll just show. It was how much? 0.5568. And if we run here, that RMSE value got increased to 1.112. Let's say why it got changed, and also we can just put one random generation line. It's called RNG 1 or 42, whatever you want, and then it will give the same results all the time. Okay, because first we got zero point 0.5, then like it got 1.1. Now if we run, so we'll get the same 0.99499, we can see. So now we can see, like earlier the noise was less, zero point 0.5 was the noise was there. Now it became 0.99. Means once we add the noise, that the accuracy also got disturbed and all. This is the like that the main purpose to show the results actually with the noise, and then without the noise. So now we'll go to the solving the surrogate metal for the compressor fluid dynamics. Compressor fluid dynamics is actually a very complex equations. It will be going to be like if you heard the name of the Navier-Stokes equation. Okay, so we'll be seeing, like let's say I have seen around the how much heat transfer happen or what is the temperature distributions and all. Now we have to see around through the through the fin. What is the flow? Or what is the which velocity that is the heat transfer is happening? Or something like flood blow, blood flow in the arteries also. We can see around, or maybe the what is the flow velocity of the coolant also we can see around. So if you see around the earlier method, they will going to use the finite difference method, or maybe the finite volume that method, or finite element method. So we can see that we have to solve the many time, one, two, three, that n number of times you have to solve it. N number of times we have to solve it. Even if we go with the finite volume method, so we have to, instead of taking the 2 points or 3 points, we can generate the volume for the each point. Again, we will be to solve for the each data points and all. Let's say I'm going to create a 100 volume points and all, so we have to do it even with the finite element method. So also we have to segregate the number of points, and then we have to do it. So it will take much more time. It's a computationally expensive also. And if you see around, so for this CFD, for incompressible fluid flow, governing equation is that governing Navier-Stokes equation is going to be like what? Del U by del T, velocity by time, plus U, convergence of the U, minus 1 by rho. Rho means that flow compressibility, and convergence plus nu upon velocity. So along with the continuity equation, so their continuity will be like before and after, their difference will be going to be a zero. Like it's like this. Okay. So now if we go to solve this equation, if we solve analytically, like using the finite difference method, finite volume methods, or finite element method, what will happen, or even the DEM also, discrete element modeling or methods, it will take time, or computationally expensive with rigid resolution and complexity. Okay. So this is the where we have to make the surrogate model, or this is the where we have to make the replacement of the this typical model to solve so that complex model. So this is where the concept of the surrogate model will help to solve the complex equation effectively. Okay. Navier-Stokes equation. So what they will do, they will try to make like Navier-Stokes equation with the flow. So we'll take one page actually. Okay. So what we'll do with the help of, we'll learn the mapping. Like how we'll do it? F of ml into x, like f of CFD into x. How will they will do it? We'll see if around and all. So in that like input can be of x, and generally it will be depends upon boundary condition or maybe the flow parameter. So what they will do surrogate model, it going to be like fast approximate of physics based simulation. So we'll take one more page. So we'll try to take some 2D example. So CFD to ML. So what will be there? Like it's going to f of xy for the ML. It's going to take from the velocity from x and y. And what they will do is that in that CFD, they will try to solve the equations using FEM, CFD, or some other methods and all. Here, we will going to give the neural network, like it's a surrogate model. Okay. So what they will do? Neural net like network f of x is equal to weight and w1 x plus b1 plus b2. And for training and all, so we have to minimize what? We have to minimize the loss. That is the root mean square 1 by n u of true minus u of predicted on square. Okay. So we'll show one example of that, like one code will be there. Surrogate model like for the CFD. It's a GD CFD. Yeah. So what they're trying to do, let's say for the NX and 50, NY is the 50, and the length in that like X direction 1, then LY is going to 1. We are going to create the X spacing and then that the linear spacing. Then after we are going to give the realistic flow model. There it's going to u into 1 minus exponential like that's going to e to power minus 5x into sine pi y plus point 0.1 sine 2 pi x plus into cos pi y. So now we are going to add some noise. So again the noise we have added already. Then after data set like we're going to create, then we have to do the normalization before giving into the that the email that the model. Then we are going to do the what I can say that train and test split. Like we have to make the training 70% and testing will be the 30%. And that's the cross validations that we are going to use it out. And we are going to give the neural that network 30 is the input layer and then that the hidden layer, and we are going to make the predictions. For that, we are going to calculate the RMSE value, then that the mean absolute error, and then R square value, and full field protection we have to do. Then we're going to see the visualizations and all. We'll see how it will look like. it's the residual plot, and this is going to be a like a distribution. So it's following the like normal distribution we can see around here, like not the exactly, but it's following the normal distribution we can see. And how it look like true what we predicted, like how the flow things are happening, but the overlapping with the it's a perfect value is coming. We can see that RMSE value is the 0.001, MAE is going to be very less, and then R square is the closer to the 1. We can see around, it's a perfect model we have generated. This data we have generated actually. So if we have that some actual problem or actual fin problems and all, so that will become that 80% or even the 70% itself R square zero point 0.7 will give the better results, because it's a very complex model and all. Now we can see how it look like. Surrogate predictions we can see around here, how the flow velocity is going to happen, and this is going to be a noisy that the measurement, and this is going to true CFD field. This is true like a CFD field. This is going to be a noise, and this is going to be a make the prediction. So we are able to predict almost same as it is what we have and all. So what happened if we could have went through the solving this field of CFD, it could have been taken some time to we have to create the that the mesh boundary size predictions and all. So it could have taken time, even the computationally expensive also. But we can see around here it took like that the fraction of the second that we got the results also. But sometime in the actual problem, if you solve around, it will take some sort of some time it will take. So there's no need to worry about like how much time it will take. It will take some time because we have to create the we have to do the comparison. What will look like actual physics based model, and then what it will look like the machine learning models and all. So now we'll go to the next problem example actually. It's called topology optimizations now. I told you like we can look for a fin. This is the things like what we have the base are there. Here thermal systems work. Okay. So someone can say we're going to expose to the atmosphere, it will going to transfer the heat. The thing is that what will happen due to that the flow and all, it will not going to effectively, it will take some time, or it will going to create a reverse impact on the system. So what will do, people are doing with the adding the fin. So fit can be of fin. It can be of rectangular also, or in the optimized way, it can go the hyperbola also, like this way. So the same way, it's a optimization, like it's a topology optimization, like it's we have to fill the material. Optimal material distribution of a structure by minimizing the objective function under the design constant topology optimization. It's something we are having the filled one. We can make the whole, but the structure integrity will be the same. Structure integrity will be same, but the thing is that optimal filling will be there. So conventional topology optimization is it's going to compliance minimization. It's something like we have to make the like it's not going to that alter the full properties of the material, or it will not alter the like strength of that one. And they are going to give the eigen, like earlier that what we have the method is a compliance minimization or eigen frequency that the maximization or design of the compliant mechanism and all. So to deal with that, what we are having now, it's a topology optimization we can see around. So what is the objective? Percentage of the volume fraction and then Poisson's ratio are the variable for the optimization and all. So this is the cantilever beam. Now we can make the optimized structure like this. Same way. So cantilever beam with the one end fixed and the other end applied to the constant load, and then optimizes the extra of the cantilever beam. Like same thing can be drawn as it is. So it will be comparatively less weight, but the strength or structure integrity will be the same. Okay. So this is the actual shape. Then we can see around there we are going to remove the like some sort of materials. Again, remove the materials. Again, this is the optimized structure came into the picture, and even we can check about the stress, strain, so that we'll be able to verify Whether we are changing it, or whether there should be no that the more stress should come into the picture, or there should be no things will should come into the pictures and all. Okay, just 1 minute. So the question will be like, what is the best possible? Inside a given domain. So if we go around with the physics based, it's going to K of rho into U is equal to F. K of rho is equal to stiffness, which depends upon the material distribution. And if we go around that, the U is called displacement vector, and F will be the force applied. So in the ideal case, stiffness will be not constant. It depends how the material is distributed. Okay. So the thing is that we have to make the optimization using the compliance is to minimize the compliance. So C is equal to F to the power 3 into U. So compliance is actually measurement of flexibility minimizing the compliance means that we are going to make the structure more stiff. No. So what they will what we will do instead of binary classification, like solid will be 1, void will be 0. So we are going to define the variable rho of x belongs to 0 to 1, and then we are going to use the simp method. It's one method that going to use in the physics actually for the topology. It's called material interpolation. It will become E of rho is equal to rho of p into E of 0. It's called E of 0 is elastic that the elasticity actually. It's called material stiffness. So the same thing now we'll see in the code also. When topology optimization with using the normal, we are going to create the one nx is equal to number of x into the like it's a 60 y into 30, like it's we are going to create the mesh grid, and then we have created the row mesh that what we have the properties of the materials and all. Then we have done the normalization and threshold the mimic topology optimization. Like it should be that going to be a less than a point of 0.03 data set that we have created. X of data, like it's a X and Y, X and Y. Then Y data is going to be row. Then we have done the normalization like before giving into the like that the ML model. And then we have done the data split for the 30% for the testing and then like 70% for the training. And we have used the which one that's called neural that network and same thing we calculated. So now we can see around how it will look like. So we can see the residual plots also that's the having very less like differences are there and error did like distribution like perfectly follow the that the normal distributions and we can see like it's a true how it becomes the predicted one like earlier that how it will look like and it's a topology that we have defined earlier itself and then we have trained into the ML model original topology that what we are having the optimized topology was there. So this is how it look like. So we can see around if the same thing what will we will going to do in the if if we solve it's required the repeated FEM analysis, iterative optimization, and then high computational cost. So means till here we were having some data or maybe the shape and all we were using for that also. Now we'll solve like let's say in this case we were having this optimization and we have generated it and then we have taken the features and then we come across the optimized topology. Now the same things optimized way we can do with the CNN also. CNN also I'll show you like how it look like. Topology optimization with using the CNN. Same way, never sample that much. Here we have designed the pattern physics in that is inspired and define the CNN with using that conventional layer 1, 2, 3. Then we have that padding will be there. Training with the using the Adam optimizations like optimization and all we can see around. So we can see how it will look like. This is a true optimization, and then here with the CNN predictive optimization and all. It's the that the results are not much clear, but the similar way we can do with the how can we go around with the what I can say. It should come some other way. We'll check with this. We have to give the flatten layer and then other layer also. Okay, fine. Now we'll go to the next or last application actually. How to solve the ODE or PDE, like ordinary differential equation or partial differential equation. So we can see around we have the yeah, that is the equation, and initial boundary condition will be there. Error will calculate, then the loss, then will feed to the feed forward network, not the back propagation. It's not the feed forward network is there. The training can be done with the back propagation. Then that the neural like network output and input can be there. So this is how things will going to work it out. Like here we'll be having x, y, z, and we'll get the time. Other things will come into the pictures and all. So this is actually not a surrogate model. We have to learn on the equation itself. It's not we don't have the data. We don't have any input and all. Here we have to do the training on the what I can say equation itself. How it will look like we'll show you. So here in classical method, we solve the ODPD by the discretizing with the finite difference method, finite element method, or finite volume. So all of them convert derivative into the algebraic equation and solve the large system. Okay. And then in contrast, the neural network, it's going to approach, assume it's a one is the one theta value the parameter. So instead of solving the equation with the grid points, we train the neural network, though it will satisfy the differential equation. That's how it will going to satisfy and all that we can see around and all. So here loss function, it will be the part of 1 by n du by dx like 1 equals plus mu u square minus of at the boundary condition. It's a residual OD like residual. This is a boundary condition. So his okay. So we'll see one example. So OD, one simple problem we'll see around, like we have the total number of generations, like we are going to generate the equations, and then x is equal to minus 1 of random number of like n of 1, time is there 1, and then nu is equal to 0.01 of pi, and then we are going to take the neural that network, we are going to use the forward pass, derivatives will be there. Then partial differential equations like f of a is equal to ut plus u into ux minus nu of u into xx. And then we are going to calculate the loss of the partial differential equation. Initial condition will be that x and t is given. And so we have to give the boundary conditions like random numbers like number from the 100 to 1. And then paste, then training and all. We can see how it will look like. It's called the physics informed neural network will be there. So it's how it will look like. One more ODE is there. Here actually we're going to use the NN and convert to die-array test grid, loss function, partial differential equation, boundary condition, initial condition and boundary condition like and then backdrop propagation. One paper was there actually, I'll just show around. See how they are doing for the CNN for the steady flow, that is the approximations and all. So this is the actually flow, laminar 2D flow, and then it's going up there. And then we are going to use the surrogate modeling in the CFD based design for the optimization. And this paper you can find out that you can get easily actually. That paper, this paper I'll keep in the like our That is a drive folder actually. CNN model is there. For the CNN model, what it actually look like? It's a like a 2D conversion decoding. Then encoding is there, and it's a discrete SDF representation for the circulation of the same. Decoding will be there. Like that is the flattened layer decoding, and then ith input, and then including loss and all will be there. And the results will be look like this is the architecture of that full CNN actually. This is how the results will get. Laminar boundary layer conditions, and then this is the predictions one, and there we can see the error actually. So we can see that the error is very less actually compared to the what we are having, the things will be here. And time cost, you can see LBM CPU, ML CPU, and that is too much difference. We can get it out and all. So this paper you can follow it up and all that you can see around. So now we'll go back to our. Now we'll solve some problems. Can anyone tell what will the answer for this? Which of the following is a key advantage of the surrogate model over conventional high fidelity models? Anyone? If you're here, then you can just see around.
B.
Yeah, can be the B. So actually, the thing is that surrogate model, if you see around the traditional methods, what they will do, they can give the accurate results. Even surrogate can give the like approximate model. That is the approximate model. It will not give like much more accurate than that. Like if there is a possibility is there. There will be some sort of error will be there. So first option we can uh, eliminate it. They are easier to develop from the scratch. No, like it's something like we are going to make the approximate model. Like the second one they require significantly less time. Yeah, obviously, because if we go with the traditional method, what they will do, they're going to create a boundary condition, then grid, mesh size, mesh convergence study, then they will do the iteration. It will take more and more time. So they always capture all physical phenomena accurately. So that are doing with the it that this can be done through the traditional method also. Okay. So that correct option is the B, not the D. So they like surrogate model actually is the fast model, approximate model, and all. So it's clear. Shall we go ahead?
Yes, sir.
Second question, what we have, I think no need to keep this one. We'll keep directly here. It's becoming very slow. Like, okay. So, when it is the appropriate to use the physics informed neural network instead of traditional methods? When it is more appropriate to use a physics informed neural network instead of traditional method. Can you tell like what is the which one is there? when the physical system can be easily solved with the standard numerical method. So, then there is no need of surrogate or physics informed neural network. So, this can be eliminated. So, where when there is abundant label data is available. So, in that case, we can go simply with the like conventional method. Is it? When dealing with the inverse problem with the limited measurement data. That's what the things like we can do in the physics inform. We can do with the when we don't know how that the mapping is there from the cause to effect or effect to cause. So we can do the inversing of the problem also. So inverse we can do. So when the governing equations are linear and well understood, so there is no need to go for no need to go for physics informed neural network. So C option is the correct option. What about third one? In a physics informed neural network formulation, what is the typically include in the loss function? I think this we have speak in the last partial differential equation. So loss will going to include the like OD residual plus boundary conditions also. Is it? Only the mean square error between the prediction and training data, it is they are going to have traditional neural network. So this can be eliminated. Only the residual of the governing differential equations also not. It can be a both. The combined error from the data fitting plus equation residual. So this is the correct option. So the error from the separate valuation data sets, no. So third option is the correct option actually. Okay. Shall we go ahead?
Yes, sir.
So in the fourth question, what we have, what technique is the common used in the physics informed neural network to compute the derivatives of the neural network output with respect to the input? Which one? Finite difference approximation. This is the again. It's going to be a like a traditional method. No need to go for the ML. Symbolic differentiation. It's again we are not going for that. Symbolic differentiation actually is like where to calculate the gradient and all, or maybe the manual like calculation of the gradient that also will not come into the pictures and all. So means automatic differentiation they will take care of now. They are going to use the automatic differentiation either back propagation or maybe the feed forward techniques and all based upon the data input and all. So, which neural network architecture is typically employed for the standard PINN implementation? Which one? CNN? No. RNN? No. Transformer network? No. That we are going to use the feed forward neural network with the multiple hidden layer. We can see around, we have seen here. We can see here. Feed forward neural network. And here we are using the automatic differentiation. Okay. Okay, we wish to solve the Helmholtz equation. It's actually like to solve the fluid problem using the PINN approach. The appropriate neural network structure should be what will be there? Three input, velocity in the x direction, velocity in the y direction, velocity in the z direction. Will be getting one output. So three input and then one output as many as layer we can do it. Is it correct? No, we can use a CNN, but no need to go for the. It's a simple x y z of the one. U is the velocity in the x direction. U velocity in the y direction. U like z in the like direction. So we can go for neural network like this. Three input, one output. In the context of the physics informed neural network solving a time dependent partial differential equation, which of the following statement is correct? For the time dependent PD, time is treated as an additional input dimension to the neural network. Yes, time cannot be handled directly and must be discrete before you know, because time is the parameter. With the time, it will change. So time cannot be handled directly. That we have to handle directly, or we have to take the majority into that. Then PNN can be solved only steady state problem, not time dependent. No, they can go for the transient also. So that we have to remove it. A separate neural network is required for the time for each step. No, we have to take all together. Velocity and then displacement or time all together. We have to train it. So first is the correct option. What about the eighth one? Which of the following describe a key challenges when implementation PINN for the complex fluid dynamics problem? Which one? PNN cannot handle the non. They can handle it actually. They can handle it better actually. So that we have to remove it. Balancing the weight between the data and physics losses. So this is the one important factor actually. PNN require explicit time stepping. No, it's a surrogate model, approximate model, approximate model. So we don't need the explicit time stepping and all. PNN cannot incorporate the bonding condition. They can incorporate boundary conditions. So balancing the weight between the data and physics losses will be the more. It should be of less compared to the what we are having other things and all. Then ninth one, when using the neural network to the solve Burger equation with the PIN approach, what could be the necessary to compute the accurate solution for the near shock formations? Which one? Anyone? So if you see around, so shock in the Borger equation, it's like UT plus UUX is equal to V of UX. So it's a sharp gradient. To resolve this, we need the adaptive or curriculum training to increase the collocation point. Collocation point is something that we are having the like flow. So one, two, three, it's a collocation point. Okay. So this in the location like it's going to, so that in that case we have to give the high resolution sampling of the collocation point. That we have to give it. Switch from the tan edge to no, it's not required actually. Adding the dropout layer to prevent the overfitting not required. So we have to give the higher resolution sampling. Just so that input should be high resolution and all. So which statement is true regarding the generalization of the capability of the physics informed machine learning technique? Which one? PIN can solve problem for the exact geometry they were trained on? No. They can solve for the any problem. Exactly. Like it can be of anyone. Parent can generalize to different bonding concept, but not different geometry. It can do for both. Okay. Physics trained with the physics constraint often generalize better than the pure data demand. Yes. So this is the third option is correct. PINN cannot generalize the outside the range of the training data under any set. No, it can generalize. Even we can without the data also they are solving the PDE or EDU. That is the ODE also. So third option is the correct option. So I think with this we have end for the today's session. And if you have any doubt till now, you can ask anything. Any doubt is there? So tomorrow there will be a session is there 6 to 8. I'll be just going to recap from the starting to the till the today. Like so that's going to be we can say the bonus lecture actually. We'll start from the like first lecture. What is that full machine learning and all. Then we'll go with the like probability optimization. Then that the neural network, deep learning, then traditional method, then advanced method we'll see, and corresponding the code also will just say like how it's going to work it out and all. So I think that's all for today. If you have any doubt,
Yes,
please
sir.
ask.
Yeah, sir. Last week also we had overlapping lecture with Parvati ma'am.
Okay. Today
We
also is
already
there, na?
we already received the link of 7 to 9 p.m.
Yeah.
So if you can manage earlier or some two different slots, that will be very helpful, sir. Because
Yeah,
revision is also must.
yeah, that I can understand. The thing is that what happened from the that NPTEL team, na, they will be going to asking for the expression of interest for the timing and all. And today was my lecture was supposed to end. So I just asked one more day to just revise it, and then I need 2 hour extra for that. And then randomly I kept 6 to 8. Like tomorrow is the holiday here, and some other commitment was there, so I just kept. And then I was not aware that 7 to 9 was lecture for her also. And today that today also she is taking the lecture. That is a extra lecture. So I don't know. This short notice I can do anything or not. Can you just put in the forum this if they can do it actually like that? Just go to the that login and all, and then you can request it actually.
Okay, sir, we'll try.
Or shall I keep the mail? I don't know because they'll be not going to entertain from my side. If you can request it, and then maybe it will help.